Hello guys, so today we have an interesting lecture, lecture 10, dual spaces. Okay, so this is a very interesting topic and a little bit abstract maybe, so please prepare to think more conceptually. There will be not too many matrices and this concrete stuff, not too many indices, but this is some abstract construction. So when you try to learn something, it's always important not only to learn the basics, but also to look at some more advanced things, because when you try to understand these more advanced things, looks at the proofs and so on, you actually understand simple things better as well. So, okay, so what is a dual space? So let me first define it, and then we will talk why it's actually interesting. So definition, let V be a vector space, vector space over F, and then V star, that's called the dual space, is a vector space of all linear maps from V to F. So like phi. So they are also called sometimes functionals. And if you are physically inclined person, people also say covectors. So this is more for physics language. So okay, so firstly, what is F? So F is a field, and when I just write F, what I mean is this is just one-dimensional vector space, which is with a basis basically. So this is just one-dimensional space isomorphic to F, and we look at all linear maps. And of course, the fact is that if phi1, phi2 are in V star, then one can define phi1 plus v2, and on a vector v, you just write it down to be equal to phi1v plus phi2v, and this we already discussed. So if you remember, we even discussed that if v and w are spaces, vector spaces, then we can look at home from v to w, just all linear maps between v and w, and this is also a vector space of dimension of this home equal to dimension of v times dimension of w. And we even talked how to think about it. This is basically this matrices, if you choose a basis in v and w. So this is a very special case when w is just one-dimensional space. So for instance, you immediately know that dimension is dimension on v and so on, but I will reprove it in a second. So before, let me give you examples. So there are lots of interesting examples. The first one, let's do something totally stupid. So you can take, say, R3, and then this is V, and then you can take the following map. So X, Y, Z goes to X. So this is a map phi, and this phi is inside V dual. Or say X, Y, Z goes to 2X plus 3 minus y, 3y minus z, and that's phi, and this is psi. This is also in V dual. And for instance, if you want to add psi and phi, this will be a map which takes x, y, z and sends it to 2x plus y, 3y minus z plus x, which will be 3x plus 3y minus z. But of course, this is a boring example. So interesting example will be something like, take for instance our vector space of polynomials. And then if you want to write down a map, you can actually use some formula. For instance, you can take phi1, which takes a polynomial p and sends it to p prime. Or for instance, you can take phi2, p prime of 0. Or say you can take polynomial p and send it to say p of 0 minus p of 1. And you see that these guys are linear maps. If you add two polynomials, these numbers will add up. And for instance, you can take phi1 plus phi2. It does something weird. It takes a polynomial and sends it to derivative at 0 plus p of 0 minus p of 1. And that's interesting. So tons of linear maps to the field one can write down. And interesting thing again is to imagine you have some vector space where there are lots of natural operations like taking derivative of a polynomial and so on, which are not general. That's not something you can do in any vector space. And then these things start to be interesting. So we will prove a few theorems about that. For instance, that v dimension of v equals to dimension of v star. And then I will say a few more interesting things, and we will discuss some fundamental examples. Okay, so main result about dual spaces is the following theorem. So let V be a vector space then dimension of V equals dimension of V star, and so V is isomorphic to V star. So that kind of sounds strange. Okay, dimensions are equal, and we know that implies that they are isomorphic. So it means basically, if you think about it a little bit, you think that, okay, there is no difference between V and V star. And that's totally wrong. So actually, the fact is that though there exists an isomorphism, there exist tons of them, and there is no special very good one. So remark, which is very important, is that there is no canonical isomorphism. So what it means I cannot tell you take a vector V and do something with it and get a vector, a map from V to F. So there is no such natural procedure, and there are lots of different particular maps, and to do them we need to choose a basis in V, and then you will choose a basis in V star, and then you can define this map. But the definition very much depends on choices. So for instance, if you have space of polynomials, there is no clear way how for a polynomial to write down any functional from polynomial somewhere. But if you choose a particular basis in V, then we can do it. Also, we, as usual, we assume for simplicity that dimension of V is finite. Also, notice a little more advanced remark. So when V is infinite dimensional space, like all continuous functions and so on, usually it starts to be not just a vector space, but what's called topological space or metric space. It has additional structure, and then it might happen that there is no natural choice of such map which is continuous, things like that. So it's all starts to be very delicate issues of functional analysis, which we are not going into, but just don't remember the fact that always V is isomorphic to V star. That's actually is useful to remember only when space is finite dimensional. Okay, so let's do that. Let's just prove it. Maybe before, just one example. So if you have V, which is just R2, and then I can take the following. I have the following map. Let me denote E1, a map in V star, where E1 takes xy vector and sends it just to coordinate x. And E2 is a map in V star, where E2 of xy just sends it to coordinate y. And then if you have absolutely any map xy to R, which will be just xy goes to ax plus by, as we know from this matrix theory, right? So we just need to write down a matrix which has one row, one column. Sorry, two columns and just one row. And then, of course, this map phi just equals to ae1 plus be2, and these two maps form a basis of V star. So that's a basis of V star, and our proof will just use this idea. So think about it for 1 minute. Okay, so let's prove the theorem. So proof. Okay, let's prove the theorem. So what's going on? So proof. So I will prove a stronger statement. So let me formulate the statement. So we show that for every basis E1, En of V, there exists unique basis E1 up to En of V star such that if you take EI and plug in inside EJ, you get 0 for I not equal to J and 1 for I equal to J. So exactly like here. So if you take basis E1, E2, then if you take in this example and look at E1 of E1, you get 1, E1 of E2 equals 0, because this is just the first coordinate of the vector E1 is 1, the first coordinate of vector E2 is 0, and E2 of E1 is 0, E2 of E2 is 1. So now I will prove that for every basis you can find another basis of the dual space having this property. So remark, so this basis E1, En is called the dual basis. So uniqueness is completely obvious. So uniqueness is obvious, and this is just because every map from V to F is determined by its values on the basis. So we have, some maps which are defined in a way what they do with each basis vector, and this determines this guys uniquely. So if you want to write them down in a matrix form, you just see that this will be a matrix 0, 0, 0, 1, 0, 0, 0. So this is just this EI of EI is 1, and all other columns are 0. So uniqueness is completely obvious from a theorem about linear maps from vector space to another vector space, and definitely such. And now let's go to existence. So existence. So such maps exist. And again, one can just say, let's take a map given by this matrix or defined by this formula, but also they have just this geometric meaning. So EI of V is just I's coordinate of V in basis E1, En. So now we need to show, so our claim is that E1 up to En is a basis of V star. So that's something we need to show. And then, of course, we know that dimension of V star equals to N. So let me erase all that part, and we'll see why this is true, and then look at some examples. Okay, so we continue the proof. So let's first prove linear independence. So for that, let's assume there exists A1 up to AN in our field, such that A1, E1 plus and so on plus AN, En equal to 0. And this I will denote by phi. So remember, it's a map from V to F. So it's a linear map, element of V star. So then, phi of E1 equals and so on equals phi of En equals to 0. So whatever vector you plug in, you definitely get 0. So let's plug in some vector. So phi of EI equals to A1, E1 of EI plus A2, E2 of EI plus and so on up to EI of EI plus and so on plus AN, EI of En. So that's all 0, because either you can think why we just defined EI upper I in a way that E upper I applied to EJ equals to 0, except for this one, and this equals to 1. Or you can just think in terms of coordinates. So this is the first coordinate of a vector EI, and this is 0. All coordinates except i's are 0. Of course, in this notation, I mean that I is greater or equals than 2, greater or equals than 3, and less than n, but yeah, probably you understand what I mean. And so, we see that phi of EI equals to AI, and we know that it equals to 0. So then A1, AN all vanish. So we see that our vectors are covectors are linearly independent. So the second part is that span of E1 up to En is a whole space V star. So they generate V star. So this is also really easy. So let's take V inside V star. So then suppose phi of E1 equals A1 and so on, phi of En equals AN. So then claim is that phi just equals to A1 E1 plus AN En. And of course this is true because I mean so this is so equality is true because it is true on the basis. So if you want to check the fact that two linear maps are equal, you can just plug in all vectors E1 up to En, one after another, and you see that phi of E1, on one hand it equals to A1, but on the other hand it equals to this A1, E1 of E1 plus TDD, because everything here is 0, this is 1, so you see this equality, and so on, up to phi of En is equal to An. And so you know that this statement is true, and so you know that these guys generate span of E1 upper indices up to En is V star. And then you see that every linear map can be presented in this way. But also you can think, so in this case, phi is just given by this, so phi is just equal to this matrix A1 up to An, and I just wrote down this matrix is a linear combination A1 times a matrix 1, 0, 0, 0, plus and so on. So that's the proof of the theorem, and you see that basically the main idea is that given a vector space and a basis, you immediately find a cool special basis of dual space, and that's what's going on here. And so, of course, our most natural question will be, what is a dual basis for every vector space we know? So let's look at our most favorite examples. Okay, so I want to discuss 3 examples. The first one is boring, and 2 others are really interesting. So example number 1. Let's just start with our most boring example, Fn. And then, of course, we have this basis E1, which is just 0, 0, 0, 0, and so on up to En, which is 0, 0, 0, 0, 1. Okay, so what is map EI? So if you take EI, and we already discussed it in the proof basically, and you apply it to vector x1 up to xn, it is just xi. So geometrically you take your n-dimensional space and it has this xi coordinate, and you just project there. So for instance, if you do R3 and then you have this 3 coordinates, so this E2, for instance, E2 is a projection on y-axis. So you just project on the line. Every point goes here, like wherever it is. It goes to the projection on the y-line. So that's the most boring example. Nothing interesting happens here. Okay, second example. So this was boring. Interesting example. So let's look at a vector space V, which will be polynomials of degree less or equal than n. So dimension, as you probably already remember, is n plus 1, and these guys are polynomials a0 plus a1x plus and so on, plus an power xn, which is p of x. So of course we know that e0 equal to 1, e1 equal to x, and so on, en equal to x power n is a basis. So what is a dual basis? So we know that dual basis, ei, of a polynomial should just return the corresponding coefficient, ai, of the polynomial. So this is a dual basis. Okay, that's not much more interesting than this one because there is an isomorphism which literally takes this story to here. But here is another way to think about it. So claim is that actually EI is the following map. EI of polynomial P equals 2, and then you take Pi's derivative at 0 factored over I factorial. And here we need to assume that we can actually divide by all numbers. So we need to assume that, let's assume that f is real numbers, complex numbers, rational numbers, something like that, not finite field. For finite field, that doesn't work because you cannot divide by p. So this is my claim, and indeed, clearly we know that p going to i's derivative of p at 0 over e factorial is linear, because for every derivative, anytime you take a derivative of a function, it's linear. When you divide by a constant, it's linear, and plug in 0, you get an element of f. And then, of course, if you take x power k i's derivative, so this equals to x power k minus I times k minus 1 up to k minus I plus 1, I guess. And so if you take this x power k i's derivative, so this is derivative, it equals to 0 for so if you take less number of derivatives than k, so for I less than k, you will get a polynomial which starts with x power something, so it's 0 at 0, sorry, it's 0, and also equals to 0 at I bigger than k, just because when you take more derivatives than the power, the polynomial completely vanishes. And x power k i's, if you take k's derivative exactly at 0, you will get k factorial. So then what it means that this ei of x power k is equal to 1 if k is equal to I, and n0 if k is not equal to I. So this is a dual basis. And then you can take any polynomial. And of course, you know that we know that a polynomial should be equal to e0 of e0 of our polynomial plus e1 of our polynomial, plus and so on. So these are coefficients now. This is kind of our a0, a1, and so on, plus n of our polynomial. But if you think what this actually means, if you just write it down, it means that our polynomial p of x equals to p of 0, which is just what e0 of p does, it just plugs in 0 times 1, plus p prime of 0 divided by 1 factorial times x, plus and so on, up to n's derivative of 0, over n factorial x power n. And this is what's called Taylor's formula. So probably in your calculus course you have come across Taylor's formula for functions, and of course it is true for polynomials. And moreover, if you take polynomial of degree less or equals than n plus first derivative will vanish. So usually Taylor's formula goes infinitely far, but for polynomial all this stuff goes away. And so this is the statement which actually is true, and this is exactly the fact that the dual basis to usual monomial basis is this interesting maps which takes i's derivative at 0 and divide by I factorial. So that's a cool example, I guess. And basically what it teaches us is that if you have a problem like here's a vector space, what is a dual basis? This problem might be an interesting problem. Okay, so let me do another example which is even more interesting than that.